From this video, we're going to discuss specific supervised decision rules or supervised classification methods. Like I mentioned in the last video, we're going to discuss several most commonly used ones. Okay, so the first one is called parallel pipette decision rule. Okay, or we simply can call it a box decision rule. So on the left side is an example. Okay, so here is a feature space formed by band A and band B. Of course, they're just for example. And several boxes have been drawn, right? Class 3, class 1, class 2, and each one includes a specific number of pixels. Of course, these pixels, they're portrayed by different shapes, so you can easily recognize them. And there are also, for each box, there is a center. For example, for class 2, we have a center here, which has a mu A2 value and mu B2 value. This is the center of the box. It's not necessarily overlapping a specific pixel, but that's it. And there is an upper and lower limits. Then there are also left and right limits for this box. It's just an example. If you do this, you can also find centers for class 3, class 1, and limits for class 3 and class 1. So this method here is very straightforward. Okay, if a pixel is included in a specific box, then that pixel belongs to that class. Okay, if pixels are found to lie in such a box, then they are assigned to that signatures class. And how to decide the size and position of these boxes based on users' knowledge of the data and signatures, prior knowledge, or based on statistics of each class collected from field work. Like I mentioned before, you can collect reference spectrum for different land covers and use these spectral characteristics to draw these boxes. So the advantage of this method is that it is pretty simple. Okay, you draw different boxes, and if a pixel is in the box, then we say that pixel belongs to that class. Very straightforward, right? And disadvantage, pixels in gap regions will not be classified. For example, those pixels represented by question marks, they are not in any boxes. So how about them? You have to leave them alone. Okay, they do not belong to any classes based on this box decision rule. And also, there are pixels in the corner of a box, or there are pixels included by 2 or even more boxes. For example, this one triangle pixel here, it is in class 2 box. It is also in class 3 box. So which one should I assign this pixel to, class 2 or class 3? So that's the problem. So there could be pixels with multiple classes assigned according to this method. So there are always pros and cons for classification methods. We'll see that later as I introduce more of them. And it will say you always have to compromise, and you always have to choose the one that is suitable for your specific application and research. There might not be perfect one, okay, but there is also a better one, or there is also a not that good one, okay? So again, there is no so-called correct and universal answers for your specific classification of an image. You have to try different methods. You have to evaluate them, and eventually you will choose the most, say, proper one or most suitable one for your application. Okay, for your specific scenario. Okay, so here is an example. Okay, so we have several classes here. Water is blue, right? Urban is red. this dark green is for forest, the brighter green is for crop. So this brown ones, okay, they're for soil, and the pink ones, they are for hazard. So which class should be assigned to pixel 2? Pixel 2 is here. Okay, urban or soil. Although pixel 2 is included in the by the box for urban, that is for sure, right? But if you compare the distance between pixel 2 to the center of urban and the distance between pixel 2 and the center of the soil, you will see that pixel 2 is actually closer to the center of soil. If we're considering this method, pixel 2 should be assigned to soil instead of urban. But on the other hand, if we are following the logic of box classification, pixel 2 should definitely be included in urban class. Okay, so you can say, like I said, it's not always perfect, but if you are carrying out box classification, then yeah, for sure, pixel 2 is definitely urban. But you should know there are also other methods to consider. Actually, the method I mentioned here about distance is another method I'm going to introduce. Okay, it's called minimum distance to means or to centers of boxes or centers of classes. So here, for example, here, this big circle here is the candidate pixel. We need to assign a class to this pixel. And what do? We calculate the spectral distance between the measurement vector for the pixel and the mean vector for each signature. So this is the position of, this is where the candidate pixel is, right? So we have mu1, mu2, mu3 as means or centers of class 1, class 2, and class 3. So now it's very easy to calculate the distance between this candidate pixel and all three centers, right? So a pixel belongs to a class W if the spectral distance to that class is the shortest. So if we compare the distance between this candidate pixel to mu1, mu2, and mu3, obviously the shortest distance is the distance between this pixel and mu2, right? So according to minimum distance to means method, we should assign class 2 to this pixel, or the other way, we should assign this pixel to class 2, right? So advantage, no unclassified pixels, because you can always calculate the distance between any pixel to any location within this feature space, right? So every pixel can be classified. There won't be any pixels like this. These pixels are represented by question marks, okay? Everyone will be classified. Everyone will be classified. And it's very fast because you only need to calculate distances, right? Disadvantage, classify those pixels which should be unclassified because they are not spectrally close to the mean of any sample. It means that according to this method, we only compare distances. We don't actually care if the shortest distance is still too long. Okay. So here is an example. So pixel 1 is right here, and we have again several classes. Okay, and we calculate the distance between pixel 1 and the centers of all classes and eventually we find the shortest distance. Sorry, it's my cat. Ugh. So here, because the distance from pixel 1 to the center of which is this crop class is the shortest, then we say that pixel 1 should be assigned to the class of crop. Okay. So next one is called k nearest neighbor. It means that in this method, when we try to find a class for a specific pixel, we need to assign a k value first. For example, if k is 1, it means that we need to draw a circle this circle should only include, of course, the center of this circle is the candidate pixel. For example, this star pixel is the candidate pixel. And say now we assign k as 5 instead of 1. See that? So what does 5 mean? It means that we need to use a circle to circle out 5 nearest pixel, or 5 nearest neighbors of this candidate pixel. For example, this circle here, it circles out 1, 2, 3, 4, 5 pixels. They are the nearest 5 neighbors of the candidate pixel. Okay, so k equals 5 right now. And we can say that 3 of these 5 pixels belong to residential. 2 of them belong to commercial. So now you have to decide if the class of this candidate pixel should be residential or commercial. So how to decide? There are different methods to decide that. For example, the simplest way to do this is finding out the majority of those 5 nearest neighbors. So we have 3 pixels for residential, 2 pixels for commercial. So the majority is residential. We can assign this candidate vector or candidate pixel to residential. Sure, you can do that. And we have another method. For example, although we have 5 neighbors here, okay, so who is the nearest neighbor? This pixel. This pixel belongs to commercial. You can do that, right? But if you do that, you say, oh, the nearest neighbor is a part of commercial. So the candidate pixel should be what? Should be commercial. You are actually carrying out nearest neighbor, because although 5 neighbors have been circled out, but you're actually using the nearest neighbor, right? So you can consider that as something called nearest neighbor, or k equals 1 nearest neighbor, right? So if you use a k nearest neighbor, we have 5 pixels, and the majority is residential. So it could be, this candidate pixel can be assigned as a residential pixel, right? We can also use something called k nearest neighbors distance weighted. What does it mean? It means that distance should be considered. These 3 pixels from residential, they're far away from this candidate pixel. On the other hand, 2 other pixels from commercial area, they're closer to the candidate pixel. According to the distance, we should assign this pixel to commercial. Of course, there are different other methods proposed for k nearest neighbor method to decide the final class of the candidate pixel. But there are 3 examples here, okay? So advantage, no assumption on the distribution of training pixels. But the disadvantage is that relatively slow because of the distance calculation to all the training pixels. You have to draw circles. Sometimes we call this circle as a buffer zone, okay, for each pixel, and calculate its distance to all other neighbors and compare them. And eventually you have to use different strategies. You have to choose one of them to decide which class this candidate pixel belongs to. Okay, so this is k nearest neighbor. So some examples here. So now we have class 1, class 2, and class 3, and this pixel in the center is a candidate pixel, right? And then say we want to assign 1 to k. So we're actually doing nearest neighbor, right? So we draw a circle to only include 1 neighboring pixel inside. So this is the result, right? So according to this method, this candidate pixel should be assigned to class 1. And of course, now we can draw a larger circle because now we assign 7 to K. So 1, 2, 3, 4, 5, 6, 7. So now we have a larger circle, and we're using 7 nearest neighbor method, right? So which class should we assign this candidate pixel to? So if we are talking about majority, it should be class 3, right? Class 3. So the next method I'm going to introduce is called maximum likelihood, but I think that will be good enough for the first week of lecture 8. Okay, I'll just stop here, and during the next week I'm going to finish this lecture. Okay, thank you.